All right, welcome back everybody. We are talking about section 6.13 of AP Calculus BC in this video. This is the second video in our series on evaluating improper integrals. And in this video, we're going to pick up where we left off from the first video. We've got a couple of more examples of improper integrals that we're going to complete here. So let's go ahead and take a look. Example 4, we're finding the integral from negative infinity to 0 of 3 over the quantity 1 plus x squared dx. That function is continuous from negative infinity to infinity. So the limit of integration of 0 and all these other finite values don't cause us any difficulties. So all we're concerned about is the lower limit of integration being negative infinity. So I'm going to go ahead and set this up as the limit as a goes to negative infinity of the integral from a to 0 of 3 over the quantity 1 plus x squared dx. All right, so I'm all set up. I find my antiderivative, so this will become the limit as a goes to negative infinity of, and the antiderivative of 3 over the quantity 1 plus x squared dx is 3 arctangent of x, which we're going to evaluate from a to 0. And so this is equal to the limit as a approaches negative infinity of 3 arctangent of 0 minus 3 arctangent of a. Okay, so 3 arctangent of 0. The arctangent of 0, where is the tangent of an angle equal to 0? That happens at 0. And as we allow a to approach negative infinity, the angle produced by the arctangent of a, if you think about what happens with the tangent as we get closer and closer to negative pi over 2, the value of the tangent gets closer and closer to negative infinity. And so the limit as a goes to negative infinity of the arctangent of a, that's going to approach negative pi over 2. And so this turns into 0 minus 3 times negative pi over 2. And boom, there's the value of our improper integral. Continuing on, example 4. The integral from 0 to 4 of the natural log of x dx is what we're going to try and find next. And we have a problem here insofar as the natural logarithm of 0 is non-existent. So we're going to turn this into the limit as a goes to 0 from the right of the integral from a to 4 of natural log of x dx. Now, the integral of the natural log is something that we're going to do using integration by parts. You know, u is equal to the natural log of x, dv is equal to dx, so v is equal to x, and du is equal to 1 over x dx. And so this becomes the limit as a goes to 0 from the right of uv, evaluated from a to 4, minus the integral from a to 4 of v du, which when I multiply these two together, it just becomes dx. And so this is equal to the limit as a goes to 0 from the right of the quantity x log of x minus x, evaluated from a to 4. Okay, so this is going to be equal to the limit as a approaches 0 from the right of 4 log of 4 minus 4 minus the quantity a log of a minus a. Okay, now, as a approaches 0, this piece right here, not a problem. That just goes to 0. As a approaches 0 from the right, this is 0, something that's approaching 0, times something that's approaching negative infinity. And so this turns into a L'Hopital's rule application to figure this out. And so I need to figure out the limit as a goes to 0 from the right of a times the natural log of a which currently is a 0 times negative infinity indeterminate form. I'm going to turn it into an infinity over infinity indeterminate form by making this the limit as a goes to 0 from the right of natural log of a over the quantity 1 over a. And then we apply L'Hopital's rule and take the derivative. This becomes the limit as a goes to 0 from the right of 1 over a over negative 1 over a squared, which is the limit as a goes to 0 from the right of, simplifying this, the opposite of a. And that limit approaches 0. So this piece also approaches 0 as a approaches 0 from the right, and therefore the value of this integral is 4 natural log of 4 minus 4. All right, continuing on. Up next, the integral from 7 to infinity of 1 over the quantity x minus 7 dx. Now this one is one where we've got two problems. We've got a problem at 7, because at 7 this function is undefined, and we have a problem at infinity. So I'm going to have to break this up and break it up into two integrals. So I'm going to pick some convenient value of x. There's not anything that particularly stands out as a convenient value of x, so I'm just going to pick some number somewhere between 7 and infinity. I'm going to go ahead and pick 10. So this is equal to the integral from 7 to 10 of 1 over x minus 7 dx plus the integral from 10 to infinity of 1 over x minus 7 dx, which is equal to the limit as a goes to 7 from the right of the integral from a to 10 of 1 over x minus 7 dx plus the limit as b approaches infinity of the integral from 10 to b of 1 over x minus 7 dx. Okay. Now, I can find the antiderivative of 1 over x minus 7 fairly easily, and so this is going to be equal to the limit as a goes to 7 from the right of the quantity natural log of the quantity x minus 7, evaluated from a to 10, and the second limit becomes limit as b goes to infinity of the quantity natural log of x minus 7 from 10 to b. And so this turns into a whole lot of stuff, but I'm just going to, look at this right now, and I'm going to say this part right here. Let's look at this part right here. Well, let's go ahead. Why not? I've got the time. Let's keep going. Limit as a goes to 7 from the right of, and this is going to be the natural log of 3 minus the natural logarithm of a minus 7. Oh boy. And look at that. This limit, as a approaches 7 from the right, this does not exist. That's a negative infinity. So this piece diverges. Therefore, the entire integral diverges. The other piece actually diverged as well. As b went to infinity, this whole expression went to an infinite value. All right, last one. Find the value of the integral from 5 to infinity of 6 over x squared minus 3x dx. If the integral diverges, state that it diverges. All right, this function is continuous over the entire interval from 5 to infinity. So the only problem here is the infinite value. So this is going to be the limit as b goes to infinity of the integral of 5 to b, from 5 to b, of 6 over x squared minus 3x dx. Oh, guess what? This is a partial fractions integration. So I'm going to have to apply partial fractions to this. My factorization of my denominator is x times the quantity x minus 3. And so a times x minus 3 plus b times x has to be equal to 6. So a plus b equals 0. Negative 3a equals 6. So a equals negative 2. B equals positive 2. And so this turns into the limit as b goes to infinity of the quantity, well, let's leave that integral sign there. Sorry about that. I got a little bit ahead of myself there. So we've got the limit as b goes to infinity of the integral from 5 to b of the quantity 2 over x minus 3 minus 2 over x dx. All right, so now I'm going to find the antiderivative of that, and this turns into limit as b goes to infinity of 2 natural log of the absolute value of x minus 3 minus 2 times the natural log of the absolute value of x, evaluated from 5 to b. b is approaching positive infinity, so in this case, both of those natural logarithms are going to be positive, so I can drop the absolute value signs, and this turns into the limit as b goes to infinity of 2 natural log of the quantity b minus 3 minus 2 natural log of the quantity b minus 2 log 2 minus 2 log 5. Okay, now these two terms here, I can factor a 2 out of that. This becomes the limit as b goes to infinity of 2 times the quantity natural log of the quantity b minus 3 minus the natural log of b. And this one, same thing, I can factor a 2 out, 2 times natural log of 2 minus natural log of 5. Okay, almost finished here. And now I can take these two natural logs right here and combine them into a single natural log. It's the natural log of the quantity b minus 3 over b. I'm going to use some logarithm properties here. The natural log of 2 minus the natural log of 5 is the natural log of 2 over 5. I'm going to go ahead and do that as well. So now, the limit as b goes to infinity. As b goes to infinity, b minus 3 over b approaches 1. And so this equals the natural log of 1 minus 2 times the natural log of 2/5. The natural log of 1 is 0, and so this is equal to negative 2 times the natural log of 2/5. We can do a lot of things with integral properties here. This could be the opposite of the natural log of 4 over 25 by making that the exponent on the natural log. And then since that's a negative first exponent, we could actually write this as natural log of 25 over 4. A lot of cool natural log stuff going on there. But we do find that this integral converges. And so, realize that when we're doing improper integrals, we can use any other integration technique that we've used up to this point. Back in example 5, we used integration by parts. In this one, we used partial fractions. We use all kinds of stuff when we're finding the value of improper integrals. Okay, that takes us to the end of this video, and this is the last video of Unit 6, so the next time I see you will be sometime in Unit 7 or beyond. All right, have a great rest of your day, enjoy yourself, and we'll see you next time. Bye-bye.